into a format which is workable. And that's what we will be discussing today. So please.
Respected committee members, research colleagues, and ladies and gentlemen, good afternoon. First of all, I welcome you all to my dissertation defense. My dissertation is on the subject of developing an autonomous condition monitoring system based on the analysis of the lifetime partial discharge data. In very brief introduction, I can tell that I used the probabilistic modeling techniques in order to come up with a solution for this research problem. These probabilistic modeling techniques actually allows us to infer the unknown quantities, make the numerical models more adaptable, learn from the historical data, and make the future predictions. A lot more will be discussed about these probabilistic modeling techniques later in my presentation. So without any further ado, let me present my research statement, the underlying research methodology, results, and the conclusions which I have actually delivered in my dissertation document. Starting off with my research problem statement. So primitively, during my literature review, which was pertaining to the partial discharge diagnostics, I realized that insulation life prognosis, that is establishing a threshold where the insulation aging is beyond the level of reliable serviceability, is one of the key research problems which needs to be examined in detail for developing an efficient and accurate diagnostic system. So that led me to devise the hypothesis of my dissertation, which was the electrical degradation of the polymeric insulation material in general can accurately be correlated with the partial discharge data patterns and the behavior, which with respect to the aging time, which can actually provide an estimated non-destructive and continuous condition assessment of the insulation. However, like implementing this continuous PD monitoring technique over an extensive wide area power system network, which consists of a myriad of electrical equipment and installations, require a hybrid technique which incorporates the efficient data acquisition system, the source identification, discrimination methods, the quantification, and the storage methodologies. So this is just to illustrate that how complex the whole PD monitoring system could be. But coming back to my dissertation, so the fundamental question of my dissertation is about whether is it possible to make diagnostic decisions concerning the insulation health based on definite distinguishable temporal PD behavior. So in order to answer this problem, I propose a solution which is the final product of my dissertation, which is the statement, the first statement, that is the variations in the fundamental partial discharge quantities and their derived variables. They must correlate as a multivariate object representing the PD intensity, overall behavior of the PD intensity with respect to the several physical discharge mechanisms taking place in the PD source. So this kind of analysis, known as the multivariable analysis, leads to the development of lifetime numerical models, which allows to learn from experimentally observed historical data and predict the temporal behavior of the partial discharge activity in general. So starting off from the fundamentals of the partial discharge mechanisms, so what actually partial discharge is? So partial discharge, as explained in the IEC standard 60270, is a localized small electrical discharge either on the surface or inside the insulation material, which may or may not completely bridge the electrodes. Here is the illustration of a partial discharge activity happening inside a cavity. As you can see, the charges are displaced within the air-filled cavity, and the partial discharge takes place across because of the lower inception voltages. These discharge pulses are actually characterized with a duration of less than 1 microsecond. So the low amplitude and the high speed transient nature of the PD events cannot be actually detected by using the conventional methods of protection or by using the novel fault location devices or the algorithms. So what's the solution? The solution is to use the high frequency sensing technologies, which actually requires to monitor the PD activity. Talking about the methods of PD monitoring, the whole PD monitoring system actually comprises of an appropriate selection, calibration, and the standard compliant recording of the PD data quantities by using various sensor technologies. Here is the illustration of a IEC standard procedure on how to measure this partial discharge activity. The test sample is represented as a capacitance CA, which is in parallel with the coupling capacitor, which is directly coupled with the coupling devices, which is, my bad, sorry. So the coupling device is actually the detection circuit, which actually observes the partial discharge quantity. And then the measuring instrument is at the end, which displays the partial discharge. Here are a few key facts which proves the effectiveness of the PD measurements as an online insulation condition assessment method. It has been reported in literature that roughly 44% of the cable faults can actually be detected by using the diagnostic methods based on the partial discharge measurements. The partial discharge diagnostics doesn't require service interruption. Another fact is, as the PD occurs before the complete breakdown, the PD monitoring actually can alarm for necessary emergent actions which can eventually avoid any kind of a catastrophic failure. These actions, depending on the severity of the degradation, could be either complete removal of the equipment from the service, necessary repair if required, or we can increase the monitoring once it triggers. The other option is to apply the parallel diagnostic techniques. These techniques then, coupled with the partial discharge diagnostics, will provide you a better understanding of the degradation. Talking back about the partial discharge activity within a cavity in particular, it has been observed that once a partial discharge has taken place, the surface charges are actually created which serve as an electron reservoir for the discharge to occur. And a typical PD aging in a single cavity follows four main stages. The first stage known for the accumulation of the charge across the surface, across the cavity surface. So during this stage, it has been observed that the chemical products or the byproducts are formed due to the continuous ionization and the ion bombardment. It also results in this surface erosion. So in addition to that, it has also been observed that the surface conductivity of the whole cavity is increased. So that actually indicates the initiation of the partial discharge activity. The next stage is known as for the stabilization period of the partial discharge. During this stage, localized big solid byproducts from the chemical reactions actually forms. As an example, the hydrated oxalic acids has been observed. These oxalic acids actually hinders the flow of the charges, and that actually stabilizes the partial discharge activity. And this phenomenon is actually more predominant in the case of polymeric insulations. After a prolonged insulation aging, electrical tree starts to develop. During this stage, very high PD intensity as well as high frequency of the partial discharge signals has been observed. And during this stage, it has been observed that the continuous partial discharge activity it's not. I will later show that how these lifetime patterns or the stages are represented. The last stage, which is always the point of interest for the researchers, is the final breakdown of the insulation. It has been reported in literature quite many times that before the insulation fails, the discharge intensity decreases to very, very low levels. Also during this stage, it has been observed the overall insulation resistance of the cable in general, which I am investigating in, also reduces. Excuse me. So in order to observe those discharge mechanisms, two independent experimental test setups were established in the high voltage laboratory. The first setup was actually established in order to acquire the initial data for the modeling purposes, and the second experimental test setup was then used for the purpose of validation of the trained algorithms. The first test setup was performed on medium voltage cable samples. They were rated for 24 kV with a reduced insulation thickness of 4.3 millimeters. These cable samples were only about 50 centimeters, so small cable samples were prepared. That was for the easiness of operation. In order to produce the artificial cavity within the insulation, needle plane geometry was used. So a sharp steel needle of a diameter 1.5 millimeter was actually penetrated into the insulation material to a depth of around 2.5 millimeters. So that will actually left with a 1.8 millimeter of the intact insulation where the partial discharge activity can progress or develops. So another thing which I did was, once I inserted the needle, I retracted the needle by 0.5 millimeter so that the air-filled cavity can be produced. So this white portion, if you can see, represents the air-filled cavity where the progression of the partial discharge activity happens. I was actually fortunate enough to actually observe the progression of the partial discharge happening inside the void. So here is the illustration after the breakdown of the cable sample. So I cut it into the thin slices of XLPE and observed that how the progression of the electrical train phenomena, which was represented as the stage 3, has progressed, and which actually results in the complete breakdown. Talking about the measurements, so I use the technique called as phase-resolved partial discharge analysis, which is a very common technique in the field of partial discharge monitoring. Here's better illustration of representing the PRPDA pattern. So here is how a commercial PD software or a system captures the PD quantities with respect to the phase, the AC phase, with respect to some definite acquisition period of time. This actual example is for 60 seconds of the acquired data. Each single dot, as you can see in there, represents the individual partial discharge quantity. One of the problems associated with the PRPDA patterns is, which actually was acknowledged in the IEC standard 60034, that states that the volume of the acquired data is one of the 3 major problems associated with the implementation of online PD measurement techniques. So I come up with a solution on how you can compress the actual data into a smaller file size. So what I did, I used the generic binary data stored by the commercial PD software and converted it into a pixel-oriented image file. So each pixel represents the intensity of the partial discharge activity happening in that particular pixel. So this figure actually represents the same data, but in the pixel-oriented image data. What's the advantage of using that image? Simple, I can use the image compression techniques to store the same data with a reduced file size while maintaining the ability to accurately reconstruct the original data as well. Very brief, I use the wavelet compression technique. Simple, it's very, it has been used in other branches of the science as well. So wavelet compression simply compress the actual image data by using this technique. Let me illustrate how I achieved the PD data compression. So the same image data, once I decrypted the data, applied the wavelet transformation, the wavelet transformation actually decomposes the original image data into a smaller number of detail coefficients and the approximate coefficients. Those coefficients then can be thresholded and quantized. So the process of the thresholding and the quantization actually reduces the number of bits required to store the original data. Finally, just to make it more compressed, I used the deflate compression and the Huffman coding to convert the image data into a single variable. And this is a 100% true compression technique, so you can reproduce the exact image data again. So you can actually make the data storage just based on this technique. So now the question is, if we have to reconstruct the original data, what we can do? Very simple, you can perform all the inverse techniques, for instance, the uncoding, the unquantization, and the inverse of the wavelet transform. Simply, you will produce the original data. The advantages, the compression results, I achieved the compression or the reduction in the file size between 92 to 96%, which is actually a very impressive result considering the fact that the PD monitoring requires a long data monitoring. So you may have like years of data, and by this technique you actually can store all of that useful data. Only thing is, like, the mean square error was in the range between 0.15 to 0.2, which is a very minimal error as well. The compression ratio, which defines how accurately or how the number of bits have been stored per image, was defined between 2 to 3%. Okay, coming back to our partial discharge study. So once I have stored the data in those compressed files, I have to actually derive few of the fundamental and the derived quantities. Two fundamental quantities, that is the apparent charge and the number of discharges, are actually necessary for formulating the 21 derivable partial discharge quantities. One of the observations I made during my research was, out of those 21 derived variables, only 4 derived variables, that are average discharge, pulse repetition rate, average discharge current, and largest repetitive magnitude, comprises a minimal set for representing the temporal PD activity. Coming to the lifetime partial discharge data. So this is an example from one of my cable samples which I used. So we used the accelerated aging. So this cable from start till the breakdown took 96 hours to form the lifetime data. The same four variables which I defined before have been represented. One problem is how we can actually see the codependency among these 4 dependent variables. So in order to answer this question, we go to the data feature or data extraction techniques. One of the techniques, very common, very useful, is known as the TSNE, T-stochastics neighborhood embedding. Utilizing this technique actually allows us to find those hidden common features or the hidden similarities among those 4 PD data variables from the last slide. These distinguishable clusters, as you can see from this data plot, in the 2-dimensional scale and the 3-dimensional scale, indicates that there is a distinguishable PD behavior happening over the insulation degradation period. What's the advantage of these dependent clusters, or the distinguishable clusters, sorry. One idea is to use those data clusters for the purpose of partial discharge modeling. So first point is the time-dependent clusters extracted from the data set of the multiple PD data variables and the observations can establish a definite set of rules and classifiers for a finite set of distinguishable classes. defining those distinguishable classes actually came from the TSNE algorithm. So the algorithm actually will suggest you how many clusters are required or how many levels of discretization is required in order to obtain these definite distinguishable classes. Another idea behind applying the partial discharge modeling is to set up a multi-experimental learning algorithm which actually modifies and corrects its output response based on the newer set of observations. So more the data you have, more accurate your learning algorithm will be. The common technique, a very useful technique in the field of machine learning is the supervised learning. So supervised learning is a method of combining all the existing data into an adaptive model for predicting the future outcomes, which actually represents the regression modeling technique, or assigning specific classes a response to a newer set of observations. And this particular represents the classification modeling technique. So both these categories can actually be merged together to perform the supervised learning algorithm. Talking about the classification modeling or the regression modeling in general. So what are the procedure for performing the classification for the classification modeling? So the classification actually requires the classifiers to assign each new observation to a specific class extracted from a finite set of classes, as I mentioned before. Coming to the response of the classification model, the same data which I showed in the previous slides has been represented with 8 distinguishable classes depending on the interdependable or the codependence of all those 4 data variables. How we can judge that how accurate is the response of the model? For utilizing this, we have to find the confusion matrix. So confusion matrix actually just compares the true class, which is based on the actual data, and the predicted class. As we can see, the class number 4 and 5 represents 100% false rate or false negative rate. So that suggests actually that the model actually fails to observe or fails to assign the class to 100% of the observations which needs to lie for these 2 classes. Similarly, the class number 7, as you can see, the 33% of the observations were falsely classified. Similarly, for the last class, 17% of the data observations were actually inaccurate. So what's the solution? How we can improve the accuracy of the classification of the regression model? One approach which I have used, known as the multi-level time series approach. So what I did, I just divided the whole lifetime data into 3 subdivisions. Why I did that step? Because these 3 subdivisions are actually in correspondence or are in accordance with the physical discharge mechanisms which I actually presented earlier. For instance, the first 50% of the degradation time actually can be classified into one model, and then from 50 to 90% of the degradation time can be represented into a second model, which actually illustrates the stage number 3. Just for reminding, what was the stage number 3? Stage number 3 was actually the inception of the electrical train. So during this stage, as you can see, the PD intensity, high PD intensity and the high frequency of the partial discharge signals has been observed. Advantage is the accuracy of our model. As you can see, by subdividing the model, we improve for the same classes, the accuracy improved to 87%. So that suggests that only 14% of the observations were wrongly classified. Okay, so that was about the classification modeling. As I mentioned before, that these models can be retrained, can be used for resume training. So what I did for 5 cable samples, which I showed at the earlier, I used all those 5 cable samples and trained the algorithm from those data observations. Here is the output response of the trained model, which is actually represented as the dots, and the colors actually represents the classification, like how the model actually classifies which observation goes to which class. And then the amplitude actually represents the regressive output, which is the predictive response or the predictive amplitude response. As you can see, and the subplot actually represents the error between the predicted response and the actual response. The actual response actually I performed a 50% validation method, which is called as the K-fold validation method. So the K-fold validation method is used for performing for judging the performance of the model of not the trained model but the self model of each cable sample. So this example is for the cable sample 1, in which the 50% validation method was used for the cable sample 1, and then it was compared with the response of the trained model for the cable sample 1. As high as 10% of inaccuracy has been observed between the true and the predictive response. And you can actually see the response here. The inaccuracy is larger when there is a transition of the discharge process. So I will illustrate further as well during this subdivision model number 2. Just before the transition period, there was a very high inaccuracy, which actually validates my approach that during this phase, during this stage between the 50% to 90%, for instance, the model predicts very accurately. It classifies very accurately as well. But just before the transition period, the model fails or produces very inaccurate results. Similarly, for the subdivision model, which is just before the final breakdown, same observations were being made. Similarly, you can see the classification model fails completely just before the breakdown and produces a very high difference in the amplitude as well. Here is a list of the pros and the cons of using the supervised learning. I will just narrate them real fast. So the classification and the regression models, they are useful for recognizing and distinguishing the different stages of the insulation degradation, as I mentioned before. So these models can be designed to be adaptive by retraining them with the newer data, set to improve the overall predictive accuracy, thereby developing a self-learned, automated, and continuous predictive system, which may be sufficient to address the objective of lifetime predictive modeling. The cons, as we see before, a maximum of 20% error has been observed in the other cable samples, which actually indicates the shortcoming of the supervised learning algorithm. Another fact, which in my opinion is the con of this technique, is the dependency of the level of discretization. So the TSNE algorithm actually dictates how many clusters you have to, how many classes you have to formulate. So one way is like you can increase the sensitivity and increase the number of the classes, which will produce a very accurate results, but it will not be distinguishable. It will be the same as the actual high-scale dimensional data. For my analysis, I used another alternative multivariate time series analysis. These kind of analysis has been used for a long time in the field of econometrics, in the field of power system analysis. So I use the same approach. I use the same approach for giving the same output response, that is the future prediction, by using this multivariate time series analysis. This technique is independent of the discretization and is independent of the classification. The advantage is that it actually understands the dynamics of the system which is represented by numerous response variables. So it actually understands that how the pattern or how the behavior is actually changing with respect to the time. Very briefly about the principle. So you have to find a linear combination of those multivariate time series analysis. These linear combinations actually converts each component series into a level of stationary. Once you obtain this level of stationary, then you can use the co-integrating relationships, and the coefficients defining those relationships, known as the co-integrating vectors, can be used for the future, can be used for the predictive diagnostics. One big con of using this multivariate time series is the unattainability for formulating a multi-experimental learning algorithm, which I suggested before for the supervised learning. So you cannot retrain this multivariate time series with a new set of observations. So it will predict individually for each given sample. However, the method of judging the accuracy of this series analysis is also different. We can use actually the Monte Carlo simulations, which actually gives you the conditional, the multiple response paths based on the residuals of the regression, and by using the conditional variances. By using the simulations, you can get the responses between 2.5 and the 97.5% percentiles, which actually gives you the 95% confidence bounds. Two approaches, the VEC and the VR model responses, were being used. Without going into details about the VEC and the VR models, how I achieved that, I can show you their response. So all those four variables represented with different colors give you the mean value between the two intervals, the percentiles, sorry, 2.5 and the 97% percentiles, and that's the actual response. Still, you can see there is an error of 5% between the predicted response and the actual response. However, this error is observed to be very minimal as compared to the 20% which was observed in the case of supervised learning. Yeah, these errors were actually found to be more prone in the case of the average discharge and the largest repetitive magnitude. So these two variables actually represents the actual intensity of the PD phenomena. Okay, I mentioned before at the start of my presentation that we performed another test setup in order to validate all those trained algorithms. So in this case, actually, we tried to observe that how these models will behave if we can apply a comparatively different type of a scenario. So we used a cable sample which was stressed with the lightning impulse voltages and the AC flashover voltages. So this cable sample was stressed on the termination end, and I observed, and I stressed it afterwards with the same configuration as you can see at the end, which is the needle plane configuration. So I was stressing, so this is the pre-stress, the termination was pre-stressed, and with the artificial aging, I used the steel needle plane configuration as well. In this configuration, I also observed the multiple PD defects. Before, it was only the internal discharge of the void. Here, we observed the surface discharge happening across this open end, and also little bit of corona as well, which actually I was able to suppress completely by using the terminating material. Anyhow, coming back to the response of the trained classifier, nevertheless, the response showed 36% of a inaccuracy between the predictive and the actual response. What's the advantage is that the model actually successfully actually classifies each observation. It improves the, sorry, my bad. So the classification accurately classifies each data observation. So the accuracy was as high as 10%, but for the regression part, the error between the predicted and the true response was as high as 36%, which tells that this model, or the trained model, requires more historical data or requires more of a learning in future. Similar observations were made for the VEC model. However, as you can see here, the actual response lies within those percentiles, as well as it was close to the mean of those percentiles as well, which actually suggests that in order to have very accurate predictive response, the VEC model represents a better scenario. Okay, that was all related to what I did in my research and the research methodology. Now let's discuss about what is the scope of this research work, where it can be applied. Recently it has been observed, or it has been stated, that the continuous condition monitoring system has gained significant importance over a traditional periodic-based monitoring system. Irrespective of what kind of sensors, what kind of measuring equipment they are using for the condition monitoring system, my research lies within this red area. First started with the data compression and the storage technique, which I proposed. Using those data compression and the storage PD data, you can use it for the electrical condition assessment in general. You can perform it for the non-destructive diagnostics. You don't have to perform any kind of a destruction on the cables, on the sample in general. Very importantly, the last step is the preemptive detection system, which actually, by using the modeling technique, the trained model technique, allows you to set the decisive rules, like a decision-making rule, which will allow you for preemptive detection system. At the end, where it can be applied. It can be applied for long-term and wide area PD monitoring system, which is one of the biggest key points in the future smart grid systems. Talking about the contributions, here's a brief summary of what I did in my dissertation document. First of all, the software-dependent raw PD data was decrypted and exploited by custom-designed algorithm for formulating different numerical lifetime PD models, as well as for the efficient PD data's preservation. A heuristic approach was actually resulted in the selection of the minimum PD data variables, which accurately represents the temporal behavior of PD activity. As I mentioned earlier, that the autonomous decision-making assessment can be performed on the insulation condition by using those trained classification of the regression analysis. Another big point in my dissertation is the subdivisions in the original model, which are recognized through the discharge theories, improves the overall model's accuracy. The last point is a key point, where the interpretation of the model responses and setting a set of decisive rules actually defines the threshold levels, which depicts a continuous and non-destructive method for estimating the condition of insulation. Talking about the future works, I still believe there is a lot to be done in the field of partial discharge monitoring. A lot of investigation has to be done. There is still a scope where you have to investigate the various scenarios to study the degradation of the polymeric insulation, which will eventually confirm the uniqueness or the universal applicability of lifetime trends, which I suggested in my dissertation. The same modeling techniques could be studied for varying insulation materials in the equipment. I used it only for the cable samples, but the same technique can actually be applied for transformers, for other switchgear equipment or other kind of equipment in general. This point, which is in the bold, which actually I'm in talk with the other research colleagues as well, which needs to be performed and needs to be performed on a larger scale, is the laboratory approach should be extended to obtain the online data from on-site equipment, which will include the background interferences and the noise, as well as the vast amount of the continuous historical PD data. Of course, the majority of that data will be uneventful because the partial discharge activity takes a long time to develop. The last point, which is more of an application of my technique. So the proposed data compression actually results in storing increased PD data volume, which will allow for its application in the wide area monitoring, as I suggested before. So therefore, merging the proposed algorithms into the real-time wide area applications requiring the hybrid techniques could improve the overall intelligent expert decision-making for multiple PD data sources. So this is actually another work which can be performed in future, where my research can be implemented. Here's the list of scientific publications. 3 articles I have submitted. They are still under the review process. Hopefully I will get a very positive response soon as well on these articles. Here's a list of the conference papers which I presented, and they all have been accepted. They have been started from my master's thesis. It continued to my PhD dissertation. I was also involved with the other groups. My professor, my research colleagues, we all have a very big group of partial discharge diagnostics. So we have actually submitted 2 papers as well, which are still under review. Hopefully they will be presented soon as well. There are 4 papers which actually are not related to the partial discharge phenomena, but I was involved in that kind of a research as well, all because of the high voltage lab, so we were able to perform this kind of research as well. That concludes my overall presentation. I appreciate all of you for listening to my dissertation. Thank you, and now I open the platform for the questions and the answers.
Thank you, Zeeshan. So yeah, this is the opportunity for the audience to ask questions, because then once you guys are done, we're going to ask you to leave, and we're going to continue this under closed doors with the committee and Z. So if you have questions, ask them now or forever hold your peace.
Please ask.
Can you go to your experimental second page?
You said experimental?
Yeah.
The first one, right? This one?
Yeah. Here you say for the XLP cable you used reduced insulation thickness. What does it mean and why did you use that?
Okay. So I was using the cable samples from another research project. That research project was actually investigating the impact of reducing the insulation thickness to 4.3 millimeters. Actually, normally for this rated cable, the thickness is around 5 millimeters. So the other research group was actually investigating that phenomena. Because of the availability of that cable sample, I used this reduced insulation thickness cable. However, based on my analysis, this will have no impact on the performance of any of my proposed algorithms. Thank you for this question, and thank you for paying attention to that. I didn't describe that in my presentation.
Correct answers, I did not discuss other customers.
I'm so sorry. I didn't know about the disclosures. Oh, Washtaba? Yeah.
Yeah. During your literature review, did you find any similar lifetime monitoring methods?
Thank you for asking this question actually. Yeah, Of course, this work has been done, but on a very different scale. One of the research team in Italy actually performed analysis of the electrical train in general, but what they did actually was the post-analysis. So, so they used the univariate analysis. So by univariate, it means only one variable was used as a stress indicator. That stress indicator was then correlated with the time to break down values. So they just use a generic inverse power law, which just give you the regression, a single variate analysis, you can say, which in my opinion has a lot of drawbacks because it will not give you the continuous condition assessment. It cannot give you diagnostics. It will just give you a stress indicator, which can actually illustrate that how the partial discharge activity intensified over the aging period. But still, my approach is on multivariate analysis, which gives you more scope or a better approach to understand the dynamics or understand the interdependability of different PD data variables. Thank you, very interesting question. Any other questions?
What was the biggest challenge you faced during your research study?
I have to keep my patience all the time because the 5 cable samples which I tested, it took me like 6-7 months to just sit in the lab and just record the data. So it required a lot of patience. And on a serious note, another aspect was establishing a corona-free test setup, which in my opinion is one of the biggest challenges everywhere. In the field, in the practical applications, you have to eliminate or suppress the corona. If you cannot suppress a corona, then it will hinder the analysis of the partial discharge in general. I remember with Professor Yoni, we started off, we used all kind of techniques to suppress the corona. It took us at least 2 or 3 months to come up with the idea of the solution, but at the end we actually used a terminating material. So it's a special material which actually suppresses or minimizes the corona behavior. Another task, the challenging one, was designing the trained algorithm. All the data from 5 cable samples, they have large variations, to be honest. They do show at least the description of 4 discharge mechanisms, but still there are variations in the magnitude as well as the responses at bigger variations, and that actually makes the whole training model technique more complex because you have to define a few set of rules or decision trees in general, and that tree is actually more